In this video, I'm going to be going through the Chapter 2 review questions from Copeland's Engineering Studies, the Definitive Guide, Volume 1, 2nd edition. We'll be looking at two questions, 16 and 17, from, they're on page 84. Okay, so this first question, we have a wheelbarrow that's being lifted up on a hill. This is a good question. You get to see these questions a fair bit. They don't tell you this angle. They don't tell you that angle. They expect you, Copeland expects you to get your protractor out and figure out that angle. But we know that the reaction is going to be perpendicular to the step and the wheel. So that at the moment that this wheel gets lifted up, at the exact moment that it's no longer touching the ground, the reaction is going to be at this location. So if we know that location, what we're doing is we're actually doing a really simple three-force method question. So what we know is we have two forces. We have the weight of the roller, and we have the tension on the handle pulling up the roller. So we know that they're obviously concurrent at that pin. The center of the mass and the tension both happen to be on that same location. So that's our point of concurrency. And if that's our point of our concurrency, we know that our third force has to join, the angle is going to be the point that joins this reaction where the thing is touching the ground, and that point of concurrency. We get the protractor out and we can figure out that our angle is 35 degrees. From that, it's not too hard to then draw this out as a scale diagram. So we've been told the weight of this thing is, we're told it's a 20 kilogram roller, and they've told us a 100 millimeter step. I don't care the 100 millimeter step. For us to be able to use the 100 millimeter step, we'd have to also know the dimensions of the wheel. So we're just going to assume that the drawing is drawn to scale. And they've told us it's a 20 kilogram roller, so that means mg is equal to 200 newtons. So I'm going to draw this vertical line here as 200 newtons. And then, there you go, 200 newtons. And then I'm drawing this at 30 degrees. It's about 30 degrees. And then I'm going to draw this one at a bit steeper than 30 degrees. Let's see. Okay, that'll do. So, if this is 30 degrees, this is 30 degrees, this is going to be 60 degrees. If this is 35 degrees, then this is going to be 55 degrees, and this is going to be 35 degrees. So that the angle here, I really should have done that addition. This one's here. This is going to be 65 degrees. Now, I could just draw this to scale, and I've kind of drawn it. I mean, I haven't got a protractor out. I should have got my protractor out, but I didn't. Yeah, it'll do. My answer, how are we going to figure this out? So we know that this is 200. So if I want to find, what have they asked us to find? Find the force P required on the handle. I've labelled it as T. I'm going to rename it now. I said T for tension, but it's, I guess, P for pulling force. P is the 30-degree angle. So we know that it's going to go this way. Remember, we're going to go tip to tail. In this case, the three forces are in equilibrium. If they're in equilibrium, that means there's no resultant. That means that the distance from where we start to where we finish is going to be 0, so it means that they're all going to add up together to be one complete triangle. So it needs to go this way in order, when that makes sense that all our arrows are going tip to tail. Okay, so to do the sine rule, what we're going to say is that we want to find P. P is our unknown. P, the opposite angle, is 55, so sine 55 degrees equals 200 divided by sine 65 degrees. Therefore, P is going to equal 200 sine 55 divided by sine 65. Okay, 200 sine 55 divided by sine 65 equals 180. and P is going that direction. With vectors, always remember to write your arrows on there. I guess there's answers. If someone, I've got a whole bunch of textbooks out there, but nobody looking at the answers. I appreciate it, Hudson. Okay, what is it? 16. 180. Okay, great. Okay, so we're going to move on to the next one. This next question, you might remember we talked about this last year. We said that if we talked about riggers, and how in riggers, when they're setting up things for cranes, so in this case I've got an object that we're lifting on the crane, and we said there's a minimum angle, not a maximum angle. If we have our crane lifting up an object with our chains like that, we're okay. But on the other hand, if we have our chains like this, we start to get worried. Why is that? Well, what we found is that if we're going to draw this as a vector diagram, so we're going to say this weight, right, mg equals, it's 10 tons, so 10 tons is 10,000 kilograms, so let's write that, so 10 plus 3 zeros for 1,000 multiplied by gravity gives us 100 newtons, 100 kilonewtons, sorry. That's a terrible zero. Okay, 100 kilonewtons. How we can draw what's happening at this location. What's happening at this location is we know that the total vertical force down is 100,000 kilonewtons. So that means that we know that the force that's going up here has to also be 100 kilonewtons. That makes sense, right? If you're lifting an object and it's all being carried by this cable, this has to equal that. Yeah? Okay, so what we know is we have, if we look at that circle, we bring that over here, what we can see in that circle is that we have a force of 100 kilonewtons, and we have two forces coming off here. We're going to call these T for tension. So if this is in equilibrium, if we have a force going up, we're going to need tension going down at this location. This might be a little bit confusing for people who haven't done trusses yet, right? For year 11s watching this video, you might just ignore those arrows. But for year 12s, you should be familiar with, okay, that makes sense. This is in tension, so it means these arrows need to be pulling down in this location in order to balance that force. The left and the right, they cancel each other out. The left and right, the left part of this is cancelled out by the right part of that. But in terms of the verticals, we know that the vertical component of this, the vertical component of T1, if I call this T1, the first Terminator movie, which is okay, right, compared to T2, which is excellent, one of the best movies ever made. We know that they're both going to be the same, so that means that this vertical component of T1, right, is going to be half of 100 kilonewtons. What's half of 100 kilonewtons? 50 kilonewtons, excellent, thank you very much. 50 kilonewtons. Okay, so if we have 50 kilonewtons as the maximum that we're allowed. Now, what we also need to know is we need to know the distances of these things, but what I want to focus on for the moment is that the angle will depend where, there will be a point where we'll have more tension on the cable than we'll actually have the weight of the box. So how I'm going to take a step back for a second. I'm going to go and we'll look at some test cases. Another way of depicting this force here is I can draw this as a vector diagram, right? What I can do is I can say, well, okay, it's going to look like this. 100 kilonewtons down, and ours is going up because of where we're looking at the cable. So this is T2 and this is T1. Now we could break that over here and we can get our shape like this. But if I told you that this was 30 degrees, if I told you this was 30 degrees, what would the interior angle be?
60.
Okay, 60. And if this is 30, then this side here is also 30. Yeah? And the same is also true there, that's already 30. So what is...
It's
an equilateral triangle. Okay, so what we know is at 60 degrees, we know that this value is going to equal that value is going to equal that value. So if we say, if the angle equals 60 degrees, T1 equals T2 equals 10 kilonewtons. But what we want to prove now is, what would happen if we went to 45 degrees? Would it be better or worse? Would the tension on these cables be bigger or smaller if we went to 45 degrees?
Bigger.
less.
Let's have a look at less. Okay, so we'll have a look why though, right? So now I'm going to draw this triangle here.
Yeah, that's a tricky part for the camera to see, but then go for it.
Okay. Okay, this angle is at 45 degrees. This angle is at 45 degrees. So that means the interior angle is also 45 degrees.
Yeah.
Yeah? This here is going to be 90 degrees, or a right angle. Right? And this one here is going to be 45 degrees. So if this is 1,000 or 100 kilonewtons, well, what's this going to be?
90 over sine 100.
Okay. This one's going to be
Wait.
100 sine 45. Can you type in 100 sine 45? I know what the answer is, but can you type it in?
70.7.
70.7. There you go. Someone's finally memorized one of these values. 70.7 kilonewtons. Okay, is that more or less than 100? It's less. And what we find is as we get steeper and steeper, we're going to get less and less, and as we go lower and lower, we're going to be taking more and more. So if we look, let's just look at it diagrammatically. If we have a really narrow angle, right? If we have a really narrow angle, right? If we go down 10 degrees, can you see how our side is now being way bigger, right? The tension side of our diagram is now way bigger. And now, if we go here, it's smaller. It's about 60%. Do you see why this angle matters? Yeah?
Yes.
So, at 10 degrees, it's dangerously high, the tension on this cable. T1 and T2 are really high.
98.4.
Okay, at 60 degrees, the tension is really low. At 45 degrees, it's less. It's about 70%. And at 30 degrees, it's now equal to the amount that you want. So that's what I mean, they give us this 55 as a bit of a red herring, right? We don't really need to know the 55 to solve this. What we can see is that when we just draw it as a vector diagram, we can see that the steeper the angle, the less load that you're going to have as tension on your cables. And as you lower the angle down, the more tension you're going to have on the cables. Now last year you guys asked me, well, why would you change this? Well, if you start to have big and tall angles like this, it does sway a little bit more, but generally good practice is you keep the angles at about 45 degrees or taller. So between 40 and 60, I would think. I'm not a rigger, but I have met a few people who worked in it, and I generally think that they would keep the angles pretty high. Okay, that's those two questions.
Please like and subscribe.